There's a little story about the periodic table. We'll go back to the early 19th century. The German chemist Johann Wolfgang Dobereiner, he proposed triads of elements. That is, three elements that had similar chemical properties. For instance, lithium, sodium and potassium. And he discovered that if you looked at their relative atomic masses, you took the relative atomic mass of lithium and that of potassium, and you took the average, you get a result very close to sodium, the middle of the two triads. If we look at the example for another one of Dobereiner's triads, which is chlorine, bromine and iodine, the relative atomic mass of iodine is 126.9. That of chlorine comes out as 35.5. Add those two together and halve them, you come out with a result of 81.2 for bromine, and the actual result is 79.9. So people began to take notice, and scientists looked at the possibility that there were patterns to the known elements. Forward a few decades, we come to the English chemist John Newlands. In a paper that he had published in 1866, he proposed his so-called law of octaves. If you put the known elements in order of relative atomic mass, you could get a pattern, a repeating pattern. For instance, starting here at lithium, count 1, 2, 3, 4, 5, 6, 7, and the eighth one, sodium, he called that an octave. Count 1, 2, 3, 4, 5, 6, 7, and you come to potassium. He published a table. However, Newlands attracted great ridicule from his colleagues, not least of which was because he made some mistakes. For instance, he put cobalt and nickel in the same family as fluorine and chlorine and bromine. Also, copper was put in the same family as lithium, sodium, potassium and rubidium. And also, other scientists objected because the known elements were expanding all the time. For instance, in the last few years before the paper was published, thallium, indium, cesium and rubidium and other elements were on their way being discovered. And Newlands took no account of this, and for this reason his colleagues rejected his ideas and he was even ridiculed. 1869 turned out to be a very eventful year for chemistry. First we'll talk about the German chemist Julius Lottermay. He published a set of tables to support the idea of what is known as laws of periodicity. In this he carried out painstaking experimentation and used also accurately known data by plotting the relative atomic mass of the elements against, on a y-axis, various physical properties. He looked at the molar volume, he looked at boiling points, and he looked at melting points, and he found there was a repetition of properties. For instance, he found the alkali metals all seem to have low melting points, and also they were similar in some ways, and also in group 7 he found their melting points seem to be fairly matched. There may well have been a trend in them, maybe a slight increase, and those elements with very, very high melting points, for instance carbon and silicon, peaked on his graphs. Now, although May was given some credit for doing this, and it also was using hard data rather than theory, the thing was, scientists were looking for a much more comprehensive system that could plot the known elements using Berzelius's symbols, and this fell to the Russian chemist Dmitri Mendeleev. Although Lottermay, the German chemist, had looked at properties such as density, boiling point, melting point and the molar volume of the elements, what Mendeleev did was he actually, again reverting back to Newlands' idea, he decided to have a look at repeating patterns again, but one more time, but much more closely. Again, he used the relative atomic masses of the known elements, but Mendeleev went much, much further. He proposed the idea that there were missing elements or undiscovered elements, and furthermore, avoiding ridicule, he decided to put gaps. And his idea of the periodic table is very, very close to our modern one. However, even he was forced to make some mistakes. For instance, these two elements here, tellurium and iodine, he knew that the relative atomic masses of the two were actually wrong in that order. In other words, the relative atomic mass of tellurium comes out as 127.6, that of iodine is 126.9. So in theory, they should be swapped around. And this didn't agree with the laws of nature for them to be placed as such. So there were still puzzling aspects. But the stars of which he left in the table, these little stars, were the missing or so-called undiscovered elements. And on this here I've listed them. Scandium, gallium, germanium, and the last one, technetium. Now, why do we remember Mendeleev? Because it's so modern what he did, because he used something which was allowing prediction to happen and also allowing for new discoveries, but also looking at the physical properties of the elements. And they had no idea in those days about the behaviour of electron orbitals or anything at a nuclear level, apart from what John Dalton had said about atoms and their combinations. And there were very accurate predictions to be made. For instance, looking at an element which had not been discovered, this element which was here by a star, which was now called germanium, he called this ecosilicon and predicted its properties, its physical properties. When the actual real element was discovered, that element was found to have properties very close to the properties that Mendeleev had predicted. For instance, this missing element here, which he called ecosilicon, he said it would be a grey metal. Germanium is greyish white. He said density of this element would be about 5.5 grams per centimetre cubed. The real one is 5.47. He said its relative atomic mass would come out about 73.4. The real element 72.6. He said its melting point would be higher than 800 degrees centigrade. It comes out at 958 degrees centigrade. And he said the metal would react with oxygen, forming an oxide with a formula of EKO2 with a density of 4.7 grams, and an oxide EKO may also exist. Sure enough, germanium exists as GeO2 with a density of 4.7, and also GeO, that is germanium combined with one atom of oxygen, is known, germanium oxide. So Mendeleev also went even further than that. He proposed an extension to periods 4, 5, 6 and 7 to allow for the fact that there should be elements occupying a separate table. Notice how he's crowded these out with these double elements in these columns. And this led to him sort of putting a far left side of the table here and a sort of another one to the far right here. Bearing in mind that what's missing on this table, I wonder if you know what it is. Misery. The missing elements from Dalton's work, Johann Wolfgang Dobereiner, Lothar Meyer and John Newlands, as well as Dmitri Mendeleev, were, of course, the noble gases. Here, on the last group, should be the noble gases. That would be helium, neon, argon, krypton, etc. Unknown, for obvious reasons, now to us, but not to them, because they are so highly unreactive. However, they're not inert. Inert means unreactive at all. Compounds were made 1962 of noble gases. Hydrogen, the lightest and most abundant element in the universe. However, on its own, it's very apt to escape from the Earth's gravity, a very fast-moving light molecule. There are 3 isotopes of hydrogen. These are atoms of the same element that have a different mass, and that's worked out as such. The bottom number tells us the atomic number, that's the number of protons. It's the same in each case. The top number is a relative atomic mass, going from 1 to 2 to 3. This tells us that the relative atomic mass, which is the number of protons plus neutrons in the nucleus, is changing. With protium, the basic form of hydrogen, just the 1 proton. With deuterium, 1 proton plus 1 neutron, making 2. In tritium, the number 3 means you've got 1 proton and 2 neutrons, 1 plus 2 being 3. I hope that explains the isotopes of hydrogen. Now, the formula of water, most of you know, it's H2O. However, there's a simple experiment that could demonstrate that this is the case. If you take some water and you add a tiny bit of acid to it in order to enable it to conduct electricity better, a so-called electrolyte, you have a battery. That's the positive terminal, that's the negative terminal. You connect the battery to electrodes. This electrode here would be the positive electrode, called the anode. The other electrode connected to the negative side would be called the cathode. You find that negatively charged ions in the water, for instance hydroxide, will be attracted to the positive electrode. Positively charged ions, protons, H+, will be attracted to the negative electrode. You should find a constant stream of bubbles forming at each electrode. At this electrode, which is the positive electrode, oxygen gas is being formed. At this electrode, which is the negative electrode, hydrogen gas is being formed. You would find, if you looked carefully at the end of the experiment, you should find roughly twice the volume of hydrogen is produced in the same time as that volume of oxygen. And this would give you a clue that the formula of water is H2O. And the actual reactions occurring at the electrode would be that the hydrogen ions are gaining electrons to form hydrogen, whereas the oxide ions, in a simplified form of the reaction, are losing twice as many to form oxygen. So you only get half as much oxygen as hydrogen. Water is a strange compound, H2O. It has this funny shape, like so, with a bond angle, which I've roughly demonstrated there, and it has a strange property that the solid, that is ice, is actually less dense than the liquid. Now that is very strange. However, that strange property of water known as this adiabatic expansion allows life on Earth to exist, because if you think about it, ice floats on water. Now that is very strange.